First of all, I would like to thank the organizers for giving me this opportunity to talk. I come from finite temperature QCD, but I will share some of my results and then I would try to motivate why it can be interesting for the EIC physics. But of course, I would like to know your feedback here on this. So my title of the talk is Chiral Anomaly and its implication for Hadron physics. So first, let me introduce to you this the problem at hand. So in QCD, the quark masses, the light quark masses, are much less than the intrinsic scale of QCD, which is lambda QCD. And when we do finite temperature, the typical scales are also temperature scales, which are also near about more than 100 MeV, which we look at. So at those scales, the masses of the light quarks are much smaller than those relevant scales. Hence, the QCD Lagrangian has a global symmetry, which is U2L cross U2R to a very good extent because the quark masses are very small. And then, since it's a unitary symmetry, one can have a, this is non-abelian, so you can have an abelian subgroup. And the special unitary part, the SU2A, we can of course recast this left and right into a vector and axial vector parts. And the SU2A cross SU2V is the non-singlet part of this chiral symmetry. And this non-singlet part actually gets broken down to SU2V through a process known as the chiral symmetry breaking. So this actually leads to presence of 3 Goldstone pions. In the limit when the masses of quarks are 0, then the pions should be massless, so exact Goldstone particles. Whereas for finite masses, these are pseudo Goldstone particles, which has a characteristic dependence that their masses are related to the square root of the quark masses. So these are pseudo Goldstone particles. And since there is a tiny mass, so this chiral symmetry breaking happens through a crossover transition, not a pure phase transition. And now from the lattice studies, we know this temperature up to very unprecedented precision, about 1%, to happen at around 156 MeV. Now, the UA1 part of it is anomalous. The vector part is of course conserved, that there is no symmetry, but we observe it in nature. But the UA1 part is anomalous, and we know this from this famous relation that the divergence of the chiral current, J mu 5, is related to a trace of, sorry, this 2del is missing here. It's related to the FF dual or the E dot B, color E dot B correlate. So, so I would like to stress here again that this non-conservation of this chiral current is essentially a non-perturbative phenomenon. So if we go back to the derivations by Fujikawa et al., then this non-conservation comes from the measure of the path integral. So the path integral measure is not invariant under this chiral symmetry, and that's why this whole term comes out. And this is essentially a non-perturbative feature which cannot be addressed through perturbation theory. So we have to do it through non-perturbative techniques, and I will use for a special technique called lattice QCD to address this. So for finite temperature, of course, this has been a very interesting problem, right from the early 80s. At that time, how much is the UA1 breaking was not known because the non-perturbative studies were at its infancy in lattice QCD. So then in the literature, these works tried to understand this through effective field theories. And there the UA1 breaking parameter was just a parameter. So one can tune it to different values and see what is the effect of these. So in these studies, one can tune these parameters, and if one puts in the UA1 breaking term to be 0 at the chiral crossover transition, then this chiral phase transition happens to be a first order phase transition, or it can be a second order depending on the amount of breaking. And then if UA1 breaking term is present at the place where chiral symmetry gets effectively restored, then of course the phase transition is of second order. but with a different universality class. So the universality class depends on the symmetry group, which also depends on this amount of UA1 breaking. So depending on UA1 breaking, the symmetry group may be just SU2 cross SU2 cross U1 or just SU2 cross SU2 vector XL vector. So the question that we would like to answer is, these are the same chiral symmetry group, but we do not know when the singlet and the non-singlet part gets effectively restored. For the singlet part, of course, it's not a symmetry, so we can only talk about its effective restoration. The question is, do the singlet and the non-singlet part of chiral symmetry gets restored simultaneously or not? That's the question that has been asked in this community for a long time. And since we saw that this UA1 part is related to the index of the gauge fields, and its origin is known to be topological. So one would also like to understand what may be the features that may give rise to this breaking. And that's why, as I mentioned, this will also, this question to this answer of how and when this UA1 breaking happens or it's effectively restored can give us answer to more fundamental questions like the topological origin of the chiral symmetry breaking. And this is how I plan to go towards the EIC, because there also we see hadron masses, and we would like to see what are the definite topological objects that cause these breaking. Now, as I mentioned, UA1 is not a symmetry. So in conventional phase transitions, there are no order parameters corresponding to this approximate symmetries. And so what happens is one actually postulates to look at this UA1 breaking or restoration by looking at hadronic correlators. So if you look at these quantum number channels, so this is for the two flavor case, so this is the delta, which is isoscalar, whereas eta is the pseudo-scalar, whereas here sigma is the scalar and pion is the pseudo-scalar particle. And when the chiral symmetry is restored, it means that these partners, the correlation functions become degenerate. Similarly, sigma and pions become degenerate. Whereas if UA1 is effectively restored, then sigma and eta should become degenerate, and also in the other side, pion and delta should become degenerate. So, to study UA1, it is important to understand the hadronic correlation function and its properties. So how do we study them? So it is a very hard problem to study. One can look at the hadronic correlation functions. One can write it in terms of inverses of the lattice Dirac operator. However, here one needs to preserve chiral symmetry to a very good extent, which is a very difficult problem on the lattice. You may have heard about no-go theorems, NISER-Ninomiya no-go theorems. And then most of the often used lattice Dirac operators only preserves a remnant of continuum chiral symmetries. If one wants to have exact chiral symmetry on the lattice, like we were hearing about overlap fermions, which Kefe has been working on for a long time, those are computationally very much expensive. For thermodynamics, we usually use staggered fermions. Here I will refer to highly improved staggered quarks, which is the HISC. And there we only have a remnant part of the chiral symmetry which is restored on the lattice. So only when we go to the continuum limit, we will get back the continuum chiral symmetries. Otherwise, only a remnant part of is there. So it is important that when we do these problems, we take the chiral, as we go to the continuum limit, do proper continuum extrapolations of all our results. That's very important. And then it is also important to check how good the chiral symmetries are preserved on the lattice. For those, we have to check the chiral word identities. So in the chiral symmetry restored phase, the chi pi minus chi delta, so here chi pi means it is the 2-point correlation function of the pion integrated over the space-time volume minus the chi delta. This is actually equal to the disconnected part of the chiral susceptibility, And in the chiral symmetry restored phase, it should be equal to the disconnected part of the chiral susceptibility. So the disconnected part coming from the correlation function of the chiral condensate. So this is one of the checks which tells us how well the chiral ward identities are satisfied. And in our studies few years back, we actually saw it with the staggered fermions, which is highly improved staggered quarks. So here this chi pi minus chi delta is my left hand side of the equation, which is shown in solid symbols. And as you go towards larger values of n tau, then you are going closer and closer to the continuum limit. And the open symbols of the same shape show this quantity, which is the disconnected piece of the chiral condensate. And what we see that when we go to final lattices beyond Tc, when chiral symmetry is restored, these two quantities shown by the closed and the open symbols match, agree with each other. So you cannot see them different here, all fall on top of each other. And they show very less sensitivity to lattice cutoff effects. So now we also tried to understand what is the origin of this UA1 breaking. So again, if one looks at the ward identities, then this topological susceptibility, this is an exact relation. Sorry, this one also comes from the ward identities. So the topological susceptibility is related to the disconnected piece of the chi 5, which is the pseudo-scalar susceptibility. But then in the chiral symmetry restored phase, these are equivalent. So the topological susceptibility is related to the chi disconnected piece of the chiral condensate times the quark mass squared. And this is the light quark mass squared that enters here. And by the chiral ward identities, it's related to the chi pi minus chi delta that I showed in the last slide. So one can calculate these two quantities independently. So these quantities can be, this disconnected piece can be calculated from the fermion-Dirac operator, the inversions of it. And the topological susceptibility can be calculated from the gluonic systems, like using FF dual operators on the lattice, but improved version of it. And the green plot shows this calculation of the topological susceptibility. This is not calculated using the 0 modes of the fermion-Dirac operator, but by doing something called Wilson flow and then measuring the E dot B integrated over the space-time volume and its correlation function. Sorry, this is the correlation function of it. This is the green plots, and this disconnected piece of the chiral condensate is measured from the inversions of the fermion-Dirac operator. And this band show the continuum limit of all these quantities as a function of temperature. And first of all, we see that these bands overlap with each other, which is a good thing because the ward identities are satisfied on the lattice when we take the continuum limit properly. And secondly, the interesting feature is that there is a change in the slope of this quantity as we increase the temperature. So if you go beyond 2 Tc, then we can parameterize this topological susceptibility as a function of temperature with this exponent b. And this b actually tells us how strongly interacting the topological constituents in the medium are. This b has been calculated in a dilute instanton gas approximation, and it is close to 2. And what we see is that for temperatures greater than 2 Tc, this dilute instanton gas approximation starts to get valid, at least in the temperature dependence of the topological susceptibility. Of course, the dilute instanton gas is not perfectly valid because there is a prefactor here which is very different when we calculate this quantity on the lattice and match it to the naive dilute instanton gas regime. But the temperature dependence is very well captured beyond 2 Tc by a dilute instanton gas. But the interesting part is that below 2 Tc, the temperature dependence is non-trivial. It cannot be explained by a simple instanton gas, and we do not know how to interpret these results yet. And within the error bars, they are quite different, and they may have different origin, which I will try to motivate why it is important in the later half of the section when I try to bring some connections with the EIC physics. Now, another way to measure these kind of hadronic correlators or the difference of it is from the eigenvalue density of the Dirac operator. So here I write the this difference in the integrated correlators in terms of the density of the eigenvalues of the Dirac operator divided by the eigenvalue squared plus the light quark mass squared. So to understand what happens to this hadronic correlator or the difference of these hadronic correlators, one has to know the properties of this eigenvalue density of the Dirac operator. And there has been very few studies on it, especially in the finite temperature context, which has been studied only recently in this paper. And in these papers and in most of the calculations in the literature, one assumes that rho is an analytic function in the eigenvalue and mass squared, and then use different word identities between the scalar and pseudo-scalar channels, and then try to characterize the functional dependence of the eigenvalue density as a function of lambda. And this calculation actually tells us that rho of lambda should go as lambda is a necessary condition for UA1 breaking to be visible in 6-point correlation function in the scalar and pseudo-scalar currents. And the question we now want to ask is the eigenvalue spectrum always a polynomial function in lambda? So in general, of course, the eigenvalue spectrum can be characterized as having a constant piece. This is the intercept of the eigenvalue density. And then there should be a linearizing part, which is linearly proportional to lambda. And this comes from the chiral perturbation theory predictions. And then there could be a lambda square dependence. And eventually it should end at the lambda cube term. And this lambda cube term is known from perturbation theory calculations. Now, I would like to show our results of the eigenvalue spectrum, which is also calculated using the highly improved staggered quarks, but with very fine lattices. So we go up to n equal to 16, which corresponds to a lattice spacing below 0.1 Fermi. And what we observe is this temperature is in the chiral symmetry broken phase. What we see is that there is a finite intercept, and then there is a linearizing part. And the intercept actually gives the chiral condensate, which we measure from this eigenvalue spectrum. And if we trust the chiral perturbation theory, then the slope is proportional to the 4th power of the chiral condensate. So this also we verify from our plot, so we can fit the results, get the intercept and the slope, and we see a good agreement with the chiral perturbation theory predictions. Now, if we go to temperatures where chiral symmetry is effectively restored, the non-singlet part of it, then of course we see that some new features come up. So of course the intercept goes to 0 because the chiral condensate also goes to 0. We are in the chiral symmetry restored phase. But then there are these small peaks that appear, and when we are in a Courcell lattice, so this n tau equal to 8 corresponds to a Courcell lattice, and as we go down or increase the n tau, then we are going to finer lattices, and we see that there is onset of a small peak of near zero modes. And then this is quite different from the bulk modes. The bulk modes again show a linear in lambda dependence, and that dependence we calculated in the from this fit in the continuum limit. So the coefficient of this term, which goes linearly as lambda, actually goes as t square. There is no mass dependence, so it should survive also in the chiral limit. So that is interesting because that tells us that UA1 breaking that comes from this kind of structure will survive in the chiral limit. And again, I would like to remind you that we do not see a lambda cube dependence at these temperatures. This temperature is where chiral symmetry is restored, but this having a lambda cube dependence was a necessary condition to have UA1 restoration also simultaneously with the non-singlet piece of the chiral symmetry group, but we don't see that happening at these temperatures. Now, one can also look at the eigenvalue spectrum in more details, because that helps us to understand how much modifications happen to the spectrum as we change the temperature. So this orange band is the probability density of the smallest eigenvalue as a function of the smallest eigenvalue. So, and this is scaled with some factor C, which depends on the chiral condensate. This is done to compare with the chiral random matrix theory predictions. So what one sees is that for temperatures lower than the chiral, in the chiral symmetry broken phase, there the distribution of the smallest eigenvalue is very similar to what one predicts from the chiral random matrix theory. Whereas if one goes to the chiral symmetry restored phase, then of course the distribution of the smallest eigenvalue changes dramatically. Of course, the agreement with the chiral random matrix theory is not exact, but the functional form is very similar. The lack of this exactness is because all these results are only valid at 0 temperature, whereas in this temperature we are very close to the chiral symmetry restoration. So we are very close to TC, but still there is quite a good dependence, quite a good agreement with the 0 temperature results. So the eigenvalue spectrum at least do not show much temperature dependence till up to the chiral symmetry restoration temperatures. And we can of course study it in more detail. So here we look at the entire spectrum, not just the single eigenvalue, the smallest one, but the entire spectrum, but scaled now with this chiral condensate. And they show this characteristic oscillations. And these oscillations are very characteristic of random matrix theory. So they show very nice oscillations. These are temperatures which correspond to the chiral symmetry broken phase. And as we go to the chiral symmetry restored phase, the oscillations are gone. So what happens is eigenvalues can be very well explained using the random matrix theory, which tells us that all the details of the interactions in the QCD-Dirac operator are not very much relevant at these temperatures. So the system is very random, and then we do not see much dependence on the details of the interaction, but it follows grossly from the predictions of our random matrix theory. Whereas if one increases the temperature, then the disorder starts to decrease. The interactions become short range between these topological constituents, and then it leads to this smearing out of all of these peaks. And interestingly, this random matrix theory is more fundamental, but people have tried to explain this in terms of some models, like even some instanton liquid like model can have similar features like a chiral random matrix theory. Now, what happens to the UA1 breaking? So we again get back to this observable, which is the difference between the correlators of pion and delta. And in this plot, we show these at different temperatures, 3 different lattice spacings. We take the continuum extrapolation. And then from the intercept, we get these black points. And then we perform a 1 by t square fit of these intercepts to see where this intercept goes to 0. So when this intercept goes to 0, then this observable should go to 0. And then we can tell that this UA1 is effectively restored, at least for these kind of correlation functions. And what we observe is that this gives a, at these temperatures which are not very far away from the chiral symmetry restoration temperature, we can perform a 1 by t square fit, which is inspired from chiral perturbation theory, and that gives a temperature about 1.15 Tc, where this UA1 is effectively restored. So, so the summary of the results till now is that from the hadronic study of the hadronic correlators, we see that the axial part of the chiral symmetry is effectively restored at 1.15 Tc. And if you want to understand it from a more microscopic perspective, it happens at the temperature where the small near zero modes of the Dirac operator gets disentangled from the bulk modes, which are the linearly rising part of the eigenvalue spectrum of the QCD Dirac operator. And now, of course, there were two aspects of this study. So first we wanted to know when this UA1 is effectively restored. For that we looked at the hadronic correlators. The second stage was we wanted to understand the hadronic correlators from a more microscopic point of view. And thirdly, we want to relate it to the topological constituents, because that is what can explain such things, which one of the ways to explain such things, the effective restoration of these kind of these kind of symmetries which are not respected in the full quantum theory. So what we observe is from the eigenvalue spectrum is that the agreement with the random matrix theory predictions actually starts to break when we go to temperatures, higher temperatures beyond and the chiral symmetry transition temperature or crossover transition temperature. So we try to interpret it, and a simple interpretation could be that one can visualize quarks at as many body states moving in the background of lowest energy topological states of gauge fields, which can be instantons, or people have talked about vortices or instanton dions, and several such candidates are there. So for temperatures in the chiral symmetry broken phase, instantons are strongly interacting, and due to which the details of the interactions are not important, so which gives rise to a disordered potential, and that's why the eigenvalue spectrum of the QCD-Dirac operator has very good agreement with the random matrix theory prediction. And interestingly, the temperature dependence is also very, very mild. So zero temperature physics can explain this physics of the eigenvalue spectrum in the chiral symmetry broken phase. So this is our conclusion: the eigenvalue spectrum can be explained in terms of zero temperature chiral random matrix theory of a certain university class. And people have tried to explain such kind of dependence. There has been attempts to understand this in terms of interacting ensemble of instantons, etc. But then one would like to understand whether these kind of topological constituents exist or not. So these instanton effects may have interesting consequences for an electron-proton collider. So originally it was discussed in the context of HERA. If one looks at these kind of chirality violating processes where one has this electron hitting a target proton, but then there is this virtual gamma which hits gluon, that gluon here, and then this gluon actually can be the gluon state can be an instanton state, which gives this chirality violating processes. So what happens is, for all these light quarks, you will have pairs of opposite chirality, QL bar, QR, for the light quarks, and then n number of gluons. So these kind of processes violate chirality. So if one only looks for one flavor of quark, suppose U quark, then it violates chirality by 2 units. And then the interesting features of such processes is that it leads to a very high multiplicity of charged and neutral particles, which comes from the fragmentation of these quarks and gluons that are produced due to these instanton effects. And in the HERA, it was discussed to look at this kinematic region, which corresponds to a range of y between 0.2 to 0.7, and the q square values, the typical values of the momentum transfer by the photon, is between 150 to 15,000 GeV square. So these kind of processes can be calculated within the instanton perturbation theory. So instanton perturbation theory is usually done in Euclidean space. So one can do this kind of calculation in the Euclidean space, do an LHZ reduction, and then one has to do an analytic continuation to the Minkowski space to relate it to the experimental results. So the typical amplitude of such processes depend on this. This d is the distribution of the radius of the instantons, and is the integral over all this radius. times the group measure, the Haar measure times the amplitude of this process, which can be calculated within the instanton perturbation theory. And the typical input that goes in such calculations is the density distribution of the instanton radii. Typically in the earlier works, people measured the calculated this in the dilute instanton gas approximation. However, since from our finite temperature results we know that the dilute instanton gas approximation gets only valid beyond certain temperature scale. If we convert those temperature scale into energy scales, then one can see that this dilute regime is only valid when the sizes of instantons are of the order of inverse of 900 MeV, which is valid for photon virtualities greater than 10 GeV. And in these calculations, of course, since this energy scale can be inverse of this energy scale can be thought of as an infrared cutoff. So then this perturbation theory calculation is almost valid. There is all these problems happened because there were no way to constrain the radius of the instantons. But now this photon virtuality actually sets a scale below which we will not see smaller instantons, and then that's why these calculations are controlled. But then lattice QCD can do much more. So on lattice, it is possible to constrain all of these topological objects and actually do a much more better evaluation of the size distribution from the lattice, and we can do it even beyond the dilute instanton gas regime and measure this, also measure the interaction measure by looking at the instanton anti-instanton separations from the lattice. So this can be done very accurately. We actually measured some of these, but I didn't want to show this result because it was done in a different context in finite temperature. But we are discussing this with my student and one of the experimentalists who is involved in, who is also involved in this EIC in the future. So actually we think that if such kind of processes can be looked at in HERA, in the upcoming EIC, it will be interesting. In HERA, it couldn't be looked for because there were no signals available for these kind of processes. But since EIC is a high luminosity device, so maybe there is some prospect to look at these processes in EIC. And from the lattice side, we can give some input on these processes. And of course, this brings to the end of my talk. So I first would like to emphasize again that the anomalous part of chiral symmetry is not a symmetry because of the quantum fluctuations. So, so it doesn't have any order parameters. The only way to study it is from non-perturbative physics and looking at Hadron correlation function. And from the finite temperature side, we now understand some of its consequences for the QCD phase transition. And the main goal now is to understand the precise microscopic origin of this effective restoration of this UO1. And if really the topological objects like instantons are responsible for it, then understanding and isolating the topological constituents is important. And EIC may have very promising prospect in this regard if one looks at chirality violating processes, which I discussed in my previous slides. Thank you very much.
Okay, so we have time for some questions. So Swagato.
Just a couple of years ago, we had a work which we looked at the UA1 restorations at, say, the climate. So we continuum, finite, infinite volume, chiral limit, all possible kind of extrapolation, everything. And we looked at the not only the eigenvalue distributions, but also its dependence on the mass by computing the derivatives with respect to mass, two derivatives. And we found that at 1.5 TC or so, it's certainly not restored. At least that's what we found. And we also found that the reason it's not, because the eigenvalue distributions really goes as m squared by computing its mass derivatives. And that arises from the non-Poissonian correlations between the eigenvalues themselves. Can you please tell us where we went wrong?
I would say not wrong, but this m square distribution, as far as I understand, comes from a dilute instanton gas approximation. And that is consistent with the earlier predictions, that we see a dilute instanton gas like prediction. But then we want to look at what is the non-trivial dependence beyond the dilute instanton gas prediction, because the dilute instanton gas prediction can go beyond to arbitrarily high temperatures. So it can go persist. And it is a very small quantity because, as you know, the temperature suppression goes as T⁻⁻8 for these kind of quantities. So it is a very strongly suppressed quantity. And the m square dependence that you discuss is a very big signature of the dilute instanton gas.
My questions are mostly, you claim that it is restored at 1.15 TC.
So this is coming from not the dilute part of it, but most of the part comes from this small eigenvalues. This is not...
At what point it is restored, it doesn't depend on what mechanism it does. My question is...
No, we wanted to look at the non-trivial part of it. The trivial part of it, the dilute instanton gas part of it, will remain there even at temperature infinity. So we are just looking at what happens, how much dependence comes from this part. Because if one looks at these quantities, chi pi minus chi delta, this 99% of it comes from these small modes.
Other questions? Everyone's tired. Okay, so what's your next steps in terms of what you're going to do and looking at physics for the IC?
So as far as I understood, we have to now go beyond the dilute instanton gas regime. So one has to look at the ensembles and try to isolate instanton anti-instanton pairs and try to get the handle on the interactions. And that is what it gets into this calculation of this quantity in the instanton perturbation theory. So one needs like the distribution, like here. One needs the distribution of the radius of the instantons as well as this amplitude. If one does, this is the amplitude, so if one does mod square of it, then this part gives, it depends on the interaction strength between the instanton and anti-instanton. So that we can constrain from the looking at the distances between instanton and anti-instanton. And the radius distribution also we can constrain very well from the lattice. Of course, it's a difficult problem, but one can do that.
Okay, so time for coffee. So thank you very much.
Thank you.